Good evening, everyone. I am Manoj Paudel from Group31. My student ID is S372470. We are excited to present our project on urban air quality and health impact analysis using machine learning and deep learning techniques. Our goal was to predict health risks arising from urban air pollution, especially focusing on pollutants like PM2.5, carbon monoxide, and nitrogen dioxide, and their effect on public health. I am joined by my colleagues Sophia and Sarisa together. We'll walk you through our project, its significance, and technical approaches we applied. Introduction. With rapid urbanization come the challenges of managing rising air pollution, which has a direct impact on public health. Pollutants like particulate matters, PM2.5, carbon monoxide, CO, and nitrogen dioxide, NO2, contribute to respiratory issues with asthma and cardiovascular problems. This project explored the link between air quality and health outcomes, using predictive modeling to support early health intervention. By applying analyzing real-world data, we hope to demonstrate how machine learning can aid in the mitigating the health risks posed by air pollution. Motivation. Our motivation for this project system from the global air crisis caused by urban air pollution. The World Health Organization report that air pollution is responsible for millions of premature deaths annually, largely due to respiratory and cardiovascular diseases. Cities are the most vulnerable to this phenomenon, and understanding the impact of air quality on health is vital for creating effective policies. Through predictive models, we can identify health risks early, enabling policymakers and healthcare providers to take prevention action that can cause save lives. Data description. Our data comes from the urban air quality and health impact data set from Kaggle. It includes over 1.7 million records from urban region between July from July 2021 to January 2020. The dataset cover air quality metrics such as PM2.5, carbon monoxide, and nitrogen dioxide, along with health indicators like hospital admission and asthma cases. We aim to correlate these pollutants with the health outcome to predict potential risks using machine learning technique. Cleaning and pre-processing this large dataset was crucial first step, as we will discuss next. Data pre-processing. To ensure the model we train will provide accurate prediction, we have to pre-process the data extensively. First, we handle the missing data through mean imputation. All missing values in the dataset were filled with zero to ensure no incomplete records. Categorical variable were encoded using label encoding, converting each category into a numerical representation. Scaling was also essential. We applied standard scaler to normalize the dataset, transferring each features to have a mean of 0 and standard deviation of 1. This scaling process ensured that the feature we on the same scale, which is essential for certain model like neural networks. We encoded a target variable Eldrick's score using label encoder to transfer it into a categorical variable for classification models. This step ensured that the data was clean, well structured, and ready for analysis. The data set was split into training 80% and testing 20%, set using test split. This ensured that the model are trained on one portion of the data and uh, eva- evaluated on unseen data to measure performance. I would like to call Sarisa to discuss about the model selection next.
Good evening, everyone. My name is Sharisa Gimire, and my student ID is S372178. Talking about the algorithm and model, for this project, we built 5 models, where 3 are machine learning model and 2 of them are deep learning model. Talking about the machine learning model, we have done it in decision tree, random forest, and naive Bayes. Each of these model has unique characteristics and handles data in different ways. Let's dive into the detail of each model. First of all, decision tree learns by splitting the data at different points based on the criterion like Gini, impurity, or entropy, aiming to create the purest possible leaf node. At each decision node, the model asks a yes-no question about the data, such as is the temperature above 90 degrees, and split the data accordingly. The strength of the decision tree lies in their simplicity. We can easily visualize the tree and understand how predictions are made. Additionally, they can handle both numerical and categorical data. However, decision tree can be prone to overfitting, especially when the tree becomes too deep. Fitting the training data too closely and performing poorly on unseen data. Talking about the random forest, it randomly selects the subset of the data and features to build each tree. This ensures that each tree is trained on different parts of data and learns slightly different patterns. The final prediction is made by taking the majority vote, that is for classification, or averaging the prediction for regression of all the trees. Random forests are highly accurate and robust to overfitting. They can handle large datasets and maintain good performance even if there are some missing or noisy data. Additionally, they can measure feature importance, which is useful for understanding which feature contribute most to the prediction. The downside of the random forest is that they can computationally expensive due to the large number of trees. Moreover, while individual trees are interpretable, the ensemble of trees make the model more complex and less interpretable compared to a single distant tree. For classification, the naive Bayes algorithm calculates the probability of each class based on the feature value and assign the class with the highest probability. It is particularly suited for tasks with categorical input, but it also works well for numerical feature with some adjustment. Naive Bayes is a simple, fast, and efficient, especially for large dataset. It requires less computational power compared to more complex model like random forest and deep learning model. Despite its naive assumption of independence, it often performs surprisingly well for classification tasks, especially when the independent assumption holds, such as in text classification or document categorization. The main drawback of naive Bayes is its oversimplified assumption and that all features are independent. In real-world dataset, features are often correlated, and naive Bayes might not capture this relationship, leading to lower accuracy compared to other models like random forest. Now, talking about the deep learning model. In addition to the traditional model learning approaches, we also explore two deep learning models: recurrent neural networks (RNN) and long short-term memory networks (LSTM). These models are designed to work with sequential or time series data, capturing the dependencies and pattern over time. Even though our dataset is not inherit, inheritedly sequential, we tested this model to see if they could capture any underlying patterns in your data quality and health risks that are not immediately obvious. The RNN processes the input sequentially, passing information from one step to the next. In each step, it looks at the current input and the hidden state from the previous state, which stores information from earlier time steps. This allows the RNN to take into the account the progression of the data over time. RNN are powerful for processing of a sequence of data where the order of the data point matters. They are often used in tasks such as time series prediction, speech recognition, and natural language processing. However, RNN struggles with long-term dependency, meaning they can have different remembering information from earlier in the sequence. This is because the information gradually fades over time as it passes through many steps in the network. The LSTM cell has three main gates: the input gate, forget gate, and the output gate. These gates allows the model to decide what information to keep, what to throw away, and what to output at each step. This structure allows LSTM to maintain information according many time steps, making them ideal for long sequences. LSTM excel at tasks that require long-term dependencies such as time series forecasting, video analysis, and speech processing. They are better equipped than standard RNN to handle the vanishing gradient problem, which makes them suitable for tasks where long-term pattern must be captured. The downside of LSTMs is that they are computationally more expensive than traditional RNN. Training LSTMs can take longer and they require more resource due to their complex architecture. Even though our data set does not have a strong sequence structure, we still tested RNN and LSTMs to explore whether they could capture any hidden relationship between air quality variables over time. For example, change in weather patterns, temperature fluctuations, humidity, and air pressure may combine over time to affect health risks in a way that isn't immediately obvious in the static model. By introducing these temporal models, we aim to see if they could uncover new patterns. Now, talking about the training and evaluation of the model, we used four core matrices: accuracy, precision, recall, and F1 score. These matrices provide a comprehensive view of how well each model is performing. And now for further presentation, I'd like to call my friend Sophia.
Good evening, everyone. My name is Sophia Vanmala, and my student ID is S372189. And in this slide, we are going to talk about the result comparison. And the decision tree model achieved an accuracy of 93.5% with a similar precision, recall, and F1 score. While it provides decent performance, the decision tree can be prone to overfitting, which might explain why its performance is slightly lower than some of the more advanced models. The random forest model performed the best, achieving an accuracy of 96.5% along with a precision, recall, and F1 score of 0.9649. As an ensemble model, random forest combines the results of multiple decision trees, which helps to reduce overfitting and improve overall accuracy. This strong performance makes it one of the best models in this project. The knife-based classifier had the lowest performance among the models, with an accuracy of 89%, a precision of 0.895, and an F1 score of 0.8917. This can be attributed to the knife-based assumption of feature independence, which likely doesn't hold well in our dataset where there may be correlations between features. The recurrent neural network (RNN) performed quite well with an accuracy of 95.5% and an F1 score of 0.955. This suggests that RNN, even though traditionally used for sequential data, we were able to capture underlying patterns in our dataset. However, they did not outperform the random forest. The LSTM model, similar to the random forest, also achieved an accuracy of 96.5% and an F1 score of 0.9649. LSTMs are particularly powerful in capturing long-term dependencies, and while our dataset isn't inherently sequential, the LSTM still managed to capture enough patterns to match the performance of the random forest. In conclusion, while all models performed reasonably well, the random forest and LSTM models stood out as the best performance with the highest accuracy and F1 scores. The decision tree and RNN models also performed well but didn't quite match the robustness of the ensemble or deep learning models. Knife-based, though computationally efficient, didn't perform as well due to its strong assumption about feature independence. These are the model comparison visualization of the same models that we discussed earlier. And this is the snapshot of the code output that we have done. So this is the code and this is the output from the code. The lines like APOS 25, 25, 27, accuracy, loss are training logs, indicating that both models trained successfully across how many APOS. Additionally, the final evaluation output at the end shows the performance matrix, accuracy, precision, recall, F1 score for both the RNN and LSTM models, confirming they were evaluated without errors. So again, going to the back to the slides. Challenges and observations. We faced several challenges during this project. So while data preprocessing, handling missing values and ensuring that the features were standardized and encoded correctly required significant effort. And during the model selection, balancing computational efficiency and performance was critical, particularly when choosing between LSTM and RNN, which are more resource intensive. And overfitting, the decision tree model was highly prone to overfitting, which is why we relied on random forest to mitigate this issue. One of our key observations is that ensemble models like random forest performed exceptionally well by reducing overfitting. Meanwhile, deep learning models such as LSTM excelled at capturing time-based patterns, making them ideal for analyzing urban air quality over extended periods. And to summarize, our analysis revealed that both random forest and LSTM are the most suitable models for predicting health risks based on urban air quality data, each achieving an accuracy of 96.5%. These models offer a balance between accuracy, precision, recall, and F1 score, making them highly effective for real world applications. In contrast, naive was less effective due to its reliance on feature independence. Ultimately, our project highlights the potential for machine learning and deep learning to address global health challenges posed by urban air pollution. By providing data driven insights, we hope to contribute to better public health intervention and urban planning policies. Thank you.